So let me introduce my dear teammates. Here's our algorithm specialist, Saha. It's our computer system architect, Andrew, and our software specialist, Connie, here. And then, so today, this is our preview for our presentation. We're going to go over a motivation of our project, use case, objective tree, functional architecture, and requirements. So essentially what we're doing is search and rescue with assisted by robots. So you might wonder, why do we use robots? So basically, if we look at the statistics, on average, there are roughly 70 firefighters die every single year. And then for those injured firefighters or with death, they get pretty much on average 1,500 and 1,500 per firefighter stipends issued every year. If you think about it, that's a lot of cost that's been taken from the government funding. And then on top of it, we have life loss. And then it is essentially because within an unknown environment, any potential unknown factor can trigger potential death. So with the current state-of-the-art technology, we can achieve higher efficiency on exploration of the unknown environment. And then most critically, the robots on top of it can collect a lot of information from the environment that can be potentially valuable, such as the map of the environment, points that with their location to help you potentially navigate around the buildings, and then to plan out such field operations. So in terms of search and rescue, basically this is a two-part of an entire lifespan of a search field operations. And then with the current state-of-the-art technology, right now leveraging our resource, we decided to target our search part.
Thanks, Zach, for the motivating the reason why robots are essential at the moment for search and rescue. Now, let me establish the use case in which we try to focus in this wide field of search and rescue. So imagine with me a unit of first responder personnel who have gotten a call to attend to any disaster, which may be any of these varied kinds. Now, they must enter the entire arena and perform this daily search and rescue operation. Now what we are providing over here is the DarkBot. The DarkBot enters the arena in the trail of the fire person. And the greatest problem over here that we're trying to address is the uncertainty. The fire person may not know what lies inside these areas. They may be unstable structures, they may be structures that are just about to fall, they may be like exploding objects that they're not aware of, they may be like hazardous signs or other sort of gases that they did not know of, and they are always risking every minute, every second inside trying to combat those kind of dangers. What we are providing and presenting over here is the DarkBot, which follows a trail of the fire person, and when the fire person is at the entrance of some really uncertain terrain or enclosure, the fire person allows the DarkBot an entrance inside, presses the deploy button, and the DarkBot goes inside and performs those violet words that we have highlighted over here. So it enters, it actively explores, and it gains the information of the objects and live transmits it to the operator. One problem that we're trying to focus over here is that disaster environments are typically the first problem that they have is that electricity goes out. The lifts are not working, the lights are not working, you cannot see. This low light is a challenge in computer vision, and this is something that we want to address because it's something that the firefighters and the first responders are facing right now. So we are also going to be working against this challenge of the dark environment and getting the information in the low light conditions. An important factor in this area of search and rescue is the human-robot interaction. That's something that, in fact, even the sub-team in the senior sub-team team had faced. We want the first responder to have active control on what the robot is doing. If the first responder thinks the robot is doing something wrong, they can actively intervene, take over the teleoperation, and again put it back into the autonomous mode. What if the first responder thinks time is critical? They have enough information about the insides and they want to intervene. They can ask it to come back to the original spot, you can go inside, perform the operation, and we want to ensure that the search spot follows them again when they go to the next site and follows them through the trail and is readily available to them whenever they want to interface inside and get information about the insights. So the storage and sending back the live location and whatever that's gathered so far is another important factor that we want to focus on in this project. We also performed a comparison with what's already out there, and we want to see what drawbacks exist and what are we filling in. So we have these firefighting robots, which as you can see is extremely bulky. These are not be expected to go inside the narrow areas, and these are not be expected to like carry or like perform these low light condition searches as well. We have the drones, which sound great, but the problem that we are additionally adding over here is that the robot has to be with the fire person throughout the entire rescue operation. These will run out of battery. Then we have the smoke bomb, which is quite inspiring. It's one of the motivators for the visibility challenge. They work in smoke, but their challenges, their drawback is that they have to be teleoperated. They do not have the intelligence, they cannot autonomously explore.
Thank you, Saha, for your use case studies. And I'll take over from the high-level goals from the use case. So here's what we envision our robot to do. The robot operates in a cluttered area, which is you can like throwing things on the floor and other kind of messed up stuff. The robot also passes through narrow corridors. And when the light goes off, the robot looks for people stranded inside the room. And along its way, it looks for useful artifacts such as like access signs and fire extinguishers and give information to the firefighters. And so having these features in hand, the robot sends messages to the firefighters. The firefighters then know which room people are stranded in, and then they can avoid places where there may be potential hazards. And we come up with an objective tree that addresses those goals. And at the top level, we specify the nature of the human-robot interaction. This links back to the fact that the robot is only meant to perform is only meant to perform search operations instead of rescue, so we need humans to intervene. We then break down into 3 sub-trees: the efficient exploration of environments, the understanding of environments, and then finally the human-robot collaboration component. We'll dive into those in the next few slides. So here's our functional architecture, and so we don't know what's going on within the DarkBot, but we know the robot is going to take environmental data as input, which includes light and temperature, and also the user commands that firefighters send in. And then as output, we return explored map, which is like easy to see, and also the visualization of humans, useful artifacts, and also potential hazards, and most importantly, the location of the robot currently at. So here's the overall functional architecture we come up with, and I'll dive into the details into 3 sub-slides. The first thing we want to do is to make sure the robot covers enough area before the stranded person is dead. So the robot has to map and localize itself, and since there are any prior map. And it should also be able to plan its path to places where the doors are open. By setting that limitation, we don't have to deal with robot manipulation to deal with the doorknobs. And the last part is the autonomous navigation feature avoids communication issues with the firefighters and enables faster response time. So here's how it works. The robot senses from its device, and then it maps the environment around it. And at the same time, it tries to localize it itself. The robot then plans for the next feasible action and moves to that position accordingly. With the new position and the new system state, the robot remaps the environment and relocalizes itself. And then this loop keeps going on until all people have been saved or the time limit has exceeded. The second thing we're doing is to understand the environment around us. It's pretty straightforward. So given low light conditions Saha just mentioned, the robot should find the objects of interest, which includes humans, useful artifacts, and potential hazards. It then communicates the data back to the firefighters to make it useful. So the robot again senses the environment, but this time it actively looks for objects of interest. And then with the map generated, it is able to localize where it is, and then it stores this information. and not yet sent back because we haven't got to that part. All right, finally, the thing we are introducing is the human-robot interface. Since we mentioned earlier that rescue operations are done by human, we want to allow users to interact with our robots. The robot takes control inputs from the first responders. The robot has a graphical interface that is easy to use. And man, do we do data visualization. The HRI part is divided into two components. So starting from the bottom, the robot accepts user instructions and passes it to the tally operation node. It then navigates back to, based on our user intention. It surpasses the autonomous planning decision node. And looking at the output, the robot returns an explored map, the visualization of humans, artifacts, and hazards, and most importantly, the location of the robot in case we want to stop the operation.
All right, thank you, Andrew. Let's continue our functional architecture with requirements. So there are three aspects in our performance requirements. It's the object detection, autonomous exploration, and local agility. So there would be two goals for each aspect, a basic one and a higher one. For the object detection, we would aim for a 90% recall for human detection and 50% recall for other objects. And for the stretch goal, we aim for a 95% and a 70%. So object detection is significantly harder than human detection. On one hand, you cannot take advantage of temperature, and on the other hand, the signs and the fire extinguishers could be anywhere in the 3D space. So for autonomous exploration, our team aimed to cover 16 square meters per minute, and our stretch goal is 21. For local agility, our team aimed to navigate and pass through a narrow space, such as doors. Our baseline target would be to navigate and pass through wider doors, such as the ones in RoboLaunch, which is 86 centimeters wide. And for our stretch goal, we aim to handle narrow doors that is just 65 centimeters wide. All of our three aspects are under low light condition, which is like 150 lux. And we have this fixed luminosity because all of the three aspects would be affected by light condition in a nonlinear way. So if our project goes well, we would probably aim get a higher goal, for example, 100 lux. All right, so that's our performance requirements. Let's continue it with non-functional ones. So our system, first of all, our system will have enough energy and computational capacity to carry out this task without any intervention. Second, our system would be able to handle failures. For example, if the network connection is lost, then our robot would automatically return home. Also, if there are any errors during program execution, our robot would just perform an emergency stop to avoid any further damages. Third, our team would make sure to design and develop the robot so it fits its work site. For example, it should be small enough to pass through doors. It should be painted with bright colors such as yellow or orange, and last, it should be lightweight enough for a human to carry it, at least for just a while. Last, our system will satisfy the need of our stakeholders. For example, the first responders would find it easy to use and easy to learn. And also for different teams, our system would be ready for any future expansion, maintenance, or reuse.
Okay, thank you, team, for the really insightful presentation. So here, let me go over what we have looked at right now. We first motivated why robot SAR is an important field. We then focused on the use case that we're trying to achieve in the Crows MRC project. We looked at the objectives tree, which helps us achieve this use case, and the functional architecture, which breaks down what the functions are and how they relate to each other. And finally, we established the performance requirements that we are going to evaluate our robots against. And we also showed the non-functional requirements that we're going to adhere to. So thank you, everyone. And I think since we have a few minutes left on our ticker, we're going to run through some interesting visuals. This is the first part of our appendix, which was a front trip to the abandoned hospital, Hawkins. The motivation of this was that if you were to build up a site at the basement of the Robo Lounge, we would like to have an idea of what kind of things we want to recreate to have like a realistic disaster hit zone. So you can have a look for yourself what the sign, symbols, and the width looks like, and what the features look like, what the debris look like, and another example of the width. I think, thank you for your attention, and we're open for any questions.